This video is all about limits, and specifically limits of rational functions or fractions. And I'll give you a little hint, most of these in this video are going to involve factoring to find the limit. Let's look at our first example, and actually you'll notice that these two look very similar. The only difference is that the problem on the left is the limit as x approaches +1, and the problem on the right is the limit as x approaches -1. Well, I'll tell you this, in any limit problem, the first thing you should always try is direct substitution. So I'm going to go ahead and do this off to the side. So the first thing I'd want to do is I would want to plug in the number that x is approaching, in this case 1. So I would have 1 squared plus 4 times 1 plus 3 all over 1 plus 1. After simplifying, you can see that that would be 8 divided by 2, or 4. Now it actually looks like direct substitution worked here. So the answer to the first limit problem, the limit as x approaches 1 of this rational function, is equal to 4. Let's take a look at what this would look like on a graph. I have gone ahead and graphed the rational function, and you can see right here as x approaches 1, you can see that the limit is in fact equal to 4, because the limit is what the graph approaches from the left-hand side and the right-hand side. And as those two values come in from both ends, you can see the graph is approaching the y value of 4. Let's take a look at the example as the limit approaches -1. Just like we did in the first example, you will want to use direct substitution first. So I would have -1 squared plus 4 times -1 plus 3 all over -1 plus 1. Once again, I am plugging in the -1 into every single x value, or using direct substitution. You can see here in the numerator, I would get 1 minus 4, which is -3 plus 3, 0 divided by 0. What I get is called the indeterminate form, 0 divided by 0. And so you may think, oh, the limit does not exist, but not necessarily. What this means is we just need to do a little bit of algebra first so that we can use direct substitution and no longer get the indeterminate form. The algebraic strategy I'm going to use here is factoring. So I'm going to factor this. Now, as I'm simplifying, I cannot lose the limit notation. If I drop the limit notation, this problem no longer is a limit problem. So this would factor, or the numerator would factor into x plus 3 times x plus 1. And if you need help with how to factor, click here so that you can watch this video to remind yourself of how to factor a quadratic. The denominator is x plus 1, and as you can see, there is a common factor to the numerator and denominator that can be canceled out. So this problem simplifies to the limit as x approaches -1 of x plus 3. Now you can use direct substitution and plug in -1 to get -1 plus 3, or the number 2. So notice that my answer was not 0 over 0 or does not exist. The limit is in fact 2. Let's go back to the graph and see what this looks like. You can see here on the graph, as x approaches -1, or as the function approaches -1 from both the left-hand side and the right-hand sides, the function is in fact approaching a y value of 2. Now you may think, wait, the function looks the same here and here, so why was this one equal to 4 and this one the indeterminate form? Well, let's look a little bit closer. As I come towards as x approaches 1, you can see that the point 1, 4 is in fact on the graph, or the function is defined at an x value of 1. As I get closer and closer to -1, you can see that as I get to -1, the function is undefined at -1, which means there is a hole. But remember, a limit is not what the function is equal to at that x value. It's what the function approaches from both the left-hand sides and the right-hand sides. You can see, in fact, the limit value is equal to 2. Let's take a look at another example. In this problem, we have the limit as x approaches -3 of x squared minus 9 all over x plus 3. Once again, you guessed it, direct substitution is always how we should start a limit problem. If I directly substitute in -3 into this problem, you can see that I would end up with 0 divided by 0. Once again, the indeterminate form. That means we must do algebra so that we can use direct substitution after we simplify. And once again, the algebra strategy I'm going to use here is factoring. Don't forget, keep that limit notation. This is the limit as x approaches -3 of, the numerator is a difference of squares, which factors into x plus 3 times x minus 3. Over the denominator of x plus 3, these factors would cancel, leaving you with the limit as x approaches -3 of x minus 3. And we met our goal. We now can use direct substitution and not arrive at the indeterminate form. So plugging in -3, we have -3 minus 3, or -6. Therefore, the limit of this rational function is -6. I would like to show you the visual of the graph so that you can see and visualize this limit. As we approach -3, you can see that the limit value approaching from the left-hand side and the right-hand side is the y value of -6. And because we arrived at the indeterminate form at direct substitution, there once again is a hole at the x value of -3. But the limit does exist. It is not undefined because the limit value is what the function approaches, which is -6. Let's take a look at one more example. In this last limit example, let's once again try direct substitution first. I have -2 cubed plus 8 divided by -2 plus 2. Or -8 plus 8, 0, divided by -2 plus 2, or 0. Once again, the indeterminate form. And I'm going to again utilize the strategy of factoring to simplify this rational function so that I can use direct substitution. Now this one may seem like a trickier factoring problem, and this numerator, x squared plus 8, is actually what's called a sum of cubes. Let me show you how to factor a sum of cubes or a difference of cubes. Here are the two factoring patterns. In our example, I have x cubed plus 8. So I have a sum of cubes. So let me write that here so that we can take a look. So mine was x cubed plus 8, and if I wanted to write that as a sum of 2 cubes, I would have x cubed plus 2 cubed. Therefore, I can see that my a value will equal x, and my b value will give me 2, and hopefully that'll help you see how we would factor this. So the first factor would be a plus b, or x plus 2. And the next factor would be a squared, or x squared in this case, minus a times b, x times 2 is 2x, and then plus b squared, or 2 squared, which is 4. And that is how the numerator would factor. So let's go back to the previous problem and fill that in for the numerator. I would have the limit as x approaches -2 of the factoring pattern I just had. Divided by x plus 2. Once again, you can see a factor cancels, which means I have a hole. Now I have the limit as x approaches -2 of a quadratic that I can use direct substitution for. So now I can directly substitute in -2. Let me go ahead and show you the algebra here on this one. And I would have 4 plus 4 plus 4, which gives me a final limit value of 12. Notice that once I do directly substitute, I can drop that limit notation because I am substituting in x at that point. Let's take a look at what this one looks like graphically. Notice after we simplified the rational function, we had a quadratic, and in fact on the graph, I can see it is the graph of a parabola. Now I'm going to have to scroll up because here I can't see exactly where it meets at -2, but if I scroll up, I can see right here that the value of the limit is in fact 12, because as I approach from both the left-hand side and the right-hand sides, the y value is 12. Once again, because that factored canceled, I do have a hole at the x value of -2, as you saw that it said undefined. Now, you can actually go back and solve each of these using what's called L'Hopital's rule. I have recorded a video on L'Hopital's rule, and if you'd like to take a look at that one, please click here to watch the video on L'Hopital's rule to see how you could do a lot of these, in fact, all of them using L'Hopital's rule as well. I hope you found this video useful. If you did, make sure to give it a thumbs up and subscribe so that you're notified as weekly math videos are posted. Thank you so much for watching.